So the second session will start with a talk by Keerthi, and she will be presenting us her study on the heat flux when we have shock wave turbulent boundary layer interaction. So Keerthi, it's up to you when you want to start. You have 20 minutes, and I will give you some notice when you have 2 minutes left. Is it okay?
Yeah, thank you. Hi, everyone.
Okay, sorry.
Can I start?
Sorry,
can I start?
15 minutes other than 20. Apologies.
Yeah, okay. Hi, everyone. My name is Keerthi JS. I'm an undergraduate student from MS Ramaiah University of Applied Sciences, Bangalore, India. My topic today is going to be about computational study of heat flux in the shockwave turbulent boundary layer interaction using SU2. This study was done under the guidance of my professor, Dr. Gopalakrishna Narayana. Looking into the presentation outlines, first we are going to look at the motivation for the present study and the research objective to be covered, basic introduction of the topic and the free stream conditions and the numerical modeling, later the discussion of the results obtained, and at last conclusion. So the motivation for the present study was basically because shockwave boundary layer interaction is prominent in the intake systems of mainly scramjet and other engines. So these interactions lead to most of the internal losses and efficiency losses. The main internal losses occurs due to the increase in the heat flux, pressure, and skin friction coefficient. Mainly the study is focused about the heat flux. The rise in the heat flux lead to the thermal loads. These thermal loads can also cause the structural damage. Here, mainly we are looking into the impinging shock model. The basic reason for choosing this model is because here the impinging shock doesn't depend upon the flow geometry on which the boundary layer is developing, unlike the case of compression wrap. And also the boundary layer is better defined over impinging shock model, and also due to the complexity involved in the boundary layer, this specific model is chosen for the study. There are three objectives to be covered in this study. One is the grid independent study. We are going to study about the grid independence and choose a model, choose a grid such that it is least computationally expensive and also gives the accurate data of the results. Second is about the validation of computational results with the experimental using the different wedge angles. This experimental validation is done for the experiment performed by Eric Skillen. And the third important point is comparison between different turbulence model, mainly using the Spalart-Almers turbulence model and Mentors-Schuster-Stansford model. Okay, for basic introduction of the topic, shockwave turbulent boundary layer interaction is a prominent phenomenon which can be seen from the transonic aircraft to hypersonic vehicles. Here, the shock generated from the shock generator hits the flat plate on which boundary layer is developed. Due to the adverse pressure gradient of the shock wave, the momentum of the boundary layer decreases, due to which the boundary layer lifts off from the flat plate, and later, after some distance, it reattaches to the boundary layer, reattaches to the flat plate, causing a suppression bubble. This suppression bubble leads to the increase of heat flux, pressure rise, temperature, and other parameters. The characteristics of this interaction mainly depends upon the incoming Mach number, nature of the impingement, flow geometry, and also the shock strength. This shockwave boundary layer interaction is also important because the shockwave boundary layer interaction takes place both externally and internally, due to which the performance and efficiency of the engines can be determined. It is basically seen in scramjets. Going to the next topic, we are looking at the free stream conditions used for the study. Here, we have chosen the incoming Mach number to be 5 and the Reynolds number to be 3.7 into 10 to the power 7 per meter. Total pressure as 2.12 megapascals, total temperature as 410 Kelvin, and wall temperature is set to be fixed to 300 Kelvin. And also the enthalpy is 0.41 megajoules per kg. The simulation is basically carried out for three wedge angles, namely 6 degree, 10 degree, and 14 degree. The shock generator has a length of 300 mm, and the length of the flat plate is used to be 1000 mm. The simulation was done using SU2. The mesh was formed by measures done by using commercially available software, and it was deformed using SU2. The quantities of the index we are looking in particular study is surface pressure, surface heat flux in terms of Stanton number. This Stanton number is basically the ratio of heat flux divided by the free stream density into the free stream velocity into Cp into the total temperature minus the wall temperature, and the class skin friction coefficient. Numerical modeling using SU2. It was the solver used here was Reynolds average Navier-Stokes equation, and we have chosen Mentor's SGS transport turbulence model. Due to the dependency of viscosity and the temperature, we have used Sutherland viscosity rather than the constant viscosity. CFL number for the fine grid is chosen to be 0.5. The spatial gradient scheme is Green-Gauss scheme, and the convective scheme used here is HLLC. The HLLC scheme is a Riemann solver mainly used in hyperbolic systems. In the presence of shock waves and other discontinuities, this scheme is widely used. At last, the convective numerical scheme is scalar upwind. On the right-hand side, you can see the domain used for the study. As you can see, the wedge and the flat plate are at a distance of 125 mm. The inlet is given, boundary condition for the inlet is given as pressure far field, and the boundary condition for outlet is given as supersonic pressure outlet present in the SU2 solvers. Here, the basic study is shown for 14 degree. That is, the distance from the horizontal to the wedge is 14 degree. Going to the next topic. Here, after performing the simulation using SU2 solver, we look into the first, the grid independent study. We have chosen three basic grids, the coarse grid of 745,000 and medium grid of 1,128,000 and fine grid of 1,482,000. The first layer spacing is 0.001 and the maximum Y plus obtained is 1.3. As you can see, the grids between the grids from the wall is done very fine to capture the heat flux and the separation bubbles very nicely. The grid independent study for across Stanton number versus the position is shown. Here we see that for the 700,000 grid, the data is not agreeing very well with the experimentally obtained data, whereas for 1.1 million and 1.5 million, the data is agreeing pretty well. But here, as we can see, since there is only slight error and due to the computational expenses, we are here choosing the 1.1 million grid cells and performing the study. Going to the next topic. Using the 1.1 grid cell domain, we are performing the study. First is the result obtained for 14-degree shock generator angle. As you can see, from the experimental optostatograph image, here the impinging shock is seen. Similarly, the impinging shock is clearly seen in the contour obtained using paraview. The expansion fans also seen here, and the compression waves and the compression waves. And the boundary layer thickness is also obtained. This boundary layer thickness in the experimental was said to be 4.7 millimeter, and as obtained by the CFD validation, at the distance of 336 mm, it is obtained to be 4.69 millimeter. There is an error of 0.01 millimeter. Since the expansion fan and the compression waves are clearly seen, this is a case of strong interaction. The next is the result obtained due to the skin friction and the heat flux. As you can see in the left hand side, the experimentally obtained and the CFD validation is agreeing very well. And whereas for the Stanton number, there is the experimental and the CFD validation is agreeing very well, except at some points. The first point is the peak. This peak is due to the amplification of the turbulence in the boundary layer. It can be attributed to the inability of the turbulence model. The second peak, as you can see here, is due to the interaction between the expansion fans and the compression waves in the later case. Except these 2 points, the results is agreeing very well. And from the graphs, you can see that the skin friction dips at some point, later increases due to the formation of compression bubble, whereas the center number increases rapidly. From here, it is clearly evident that the Reynolds analogy is not satisfied. According to Reynolds analogy, the Stanton number must be exactly the or approximately the half of the skin friction coefficient. As you can see, the Stanton number is up to about 6 into 10 to the power minus 3, and whereas the skin friction coefficient obtained is about 10 into 10 to the power minus 3. As you can see, it is not exactly half of the skin friction coefficient. Next, going to the pressure graph. As you can see, the pressure due to the strong interaction case, it is rising up to 91.6%. And this pressure is agreeing very well with pressure obtained from the simulation agreeing very well with the experiment performed. In the last graph, we talked about the dissatisfaction of the Reynolds analogy. This dissatisfaction of Reynolds analogy can also lead to the formation of complex non-equilibrium turbulent interacting fluids. This indicating that the application of Brand solver is not enough. Next, going into the result and discussion of shock generator angle of 10 degree. Here, as we can see, though there is a clear-cut evidence of impinging shock, expansion fan, and a compression waves, and similarly in the simulation contour, but this is showing that suppression bubble is small and indicating it is a medium interaction case, and the interaction is not as strong as a 14-degree shock angle case. The skin friction and Stanton number graph is also obtained here. As in the case of 14-degree shock generator, here also the Reynolds energy is not satisfied, and here also for the Stanton number there is a peak seen, which is the amplification in turbulence in the boundary layer. As you can see, the results are agreeing very well with the experimentally obtained results by Eric's scale. Lastly, the pressurization. Here, the pressure is about 3.5 kilopascal, 3.5 10 to the power 4 pascals. From the shock generator case of 14 degree, in comparison with the shock generator of 10 degree, we see that as there is a decrease in the shock generator angle, there is also decrease in the pressure. Thus indicating that the greater is the shock generator angle, the stronger is the interaction, and high is the pressure and high is the heat flux in terms of Stanton number obtained. Next, we will look into the results of 6-degree wedge angle case. In 6-degree wedge angle case, there is no clear distinction between the expansion fan and the compression wave, as you can see in both the diagrams. Here also, the separation bubble is very small and we can hardly see the separation bubble. This is a weak interaction case. Going into the graph of skin friction and Stanton number, we see that both shows similar flow physics, and the value of Stanton number is 1.8 into 10 to the power minus 3, whereas the value of skin friction is 3.5 into 10 to the power minus 3. Thus, the Stanton number is exactly the half of the skin friction coefficient obtained, thus indicating that the Reynolds analogy is satisfied and there is no non-equilibrium interaction seen in the case of 6 degree.
You have 2 minutes left.
Yeah. The next is a case of surface pressure. As you can see, the surface pressure is increasing to 2 into 10 to the power minus 4. This is very less compared to the surface pressure obtained in 10 degree and 14 degree case. After the CFT validation, at last we'll look into the comparison between different turbulence models. Here, mainly we have taken the Spalart-Almaz turbulence model, which is a one equation model, which mainly solves for kinematic viscosity. And second one is shear stress transport model, which is a two equation model solving for turbulent kinetic energy and specific dissipation energy. As you can see, the skin friction coefficient graph, the results obtained by the Spalart-Almaz turbulence model and the shear stress transport model agrees approximately well with the experimentally obtained results. As for the pressure, the SST model predicts the pressure better than the SA model, thus indicating that SST model is better at prediction whenever there is a suppression bubble present. Going mainly into the heat flux, as you can see from the graph, the SST model predicts the point of the separation correctly with the experimental obtained result, whereas the SA model, it has some errors to predict the point at which the flow separation occurs. There is a big difference between the SST model and SA model, though the error is less in the SA model. Since SA model doesn't include a turbulent kinetic energy calculation or turbulent dissipation energy calculation, it doesn't have turbulence amplification in the boundary layer. Whereas in case of SST, both the turbulent kinetic energy and turbulent dissipation energy is solved, due to which the turbulence amplification in the boundary layer can be seen. Also, due to the fact of the constant Prandtl number of lambda Prandtl number and turbulent Prandtl number, these variations can be seen. In the right-hand side, you can see the difference in the separation bubble. This you can see that though there is a clear-cut distinction, the expansion wave from the separation bubble in the shadogram is agreeing very well with the SST turbulence model rather than the SA turbulence model, thus indicating that SST is better to be applied than the SA turbulence model whenever there is a separation of flow present. The further study of SA and SST turbulence model and other turbulence model is also required. Okay. Concluding the work, in this present study, we have performed the CFD validation case for 3 wedge angles, mainly 6 degree, 10 degree, and 14 degree. And as we see that as the shock generator angle increases, there's an increase in the heat flux. If there's an increase in the heat flux, which leads to the increase in the thermal loads and also the structural damage of the engines and the inlet systems. We have seen in the 14 degree and 10 degree case that skin friction coefficient and the Sandel number doesn't agree the Reynolds law energy, leading to the complex non-equilibrium behavioral turbulent interacting fluids. And also, since the turbulence model does not include the effect of acoustic waves coming from the boundary layer, and as stated by Eric Skilling in his research paper, this can be the reason for a high peak in the heat flux as seen. Thus, the similarity loss like Reynolds energy is not applied in the case of strong interaction cases. The negative skin friction as seen in the graphs is due to the recirculating or the reversal of the flows. At last, the amplification is due to amplification of the turbulence in the boundary layer region due to strong shock as well as a high surface pressure may be the reason of high heat flux, which need to be reduced. The reduction in the interaction and the reduction in the heat flux can be done by a tangential blowing or by suction blowing, where we basically place the orifice plate. Thus, concluding the work, the SU2 solver is very well proven to predict the heat flux very well compared to the other commercially available softwares. Going into the future works, here the future works the future work of this shockwave turbulent boundary interaction is to work on the unsteady Rance equation and to get the FFT of it and to work on the acoustic phase coming from the boundary layer. Second is, since the Reynolds analogy is not satisfied in 14 degree and 10 degree case, and which leads to the indication of complex non-equilibrium turbulent reacting flows, we to apply the Nemo solver to solve this this dissatisfaction is also seen. At last, to work on the 3D cases of swept shock generator angle is also the future work. Thank you.
Thank you very much for your talk. We have actually only 2 minutes left for questions. So is there any question from the audience? Yes, there is one question.
Yeah.
I will repeat the question afterwards.
Hi, and thank you for
Okay, I will repeat the question for the benefit of the people online. The question is asking if the comparison between the numerical simulations and the experimental data are also including the error bars that can go with some uncertainty with the experimental measurements. Is it the correct question? Okay, please, I leave it to you to answer.
The experimental results are as performed by Eric Skilling were obtained from his research papers, and yeah, the numerical simulation also includes the errors, or it including the errors by the experiments and by the numericals. Everything is done and it is presented over here.
Yes, could you please repeat the last part? It was not coming out very clear from the audio.
Yeah. since the experimental results were taken from the research paper by Eric Skulin, it is compared with the simulation result obtained by us. So everything is included in it. The error, there is nothing filtered out in that.
Okay. We have 1 minute for one last quick question. Yes.
Hi, thank you, Tom. Just kind of following up from the previous question. You showed a slide where you have quite large differences between the experimental subscription coefficient and the subscription coefficient like SU2. Do you think that could be because of the boundary conditions? Because if I remember correctly, using fixed wall temperature, it's natural cooling on the wall based on temperature.
Yes, so I would repeat the question, and the question is looking after the discrepancies between some of the experimental and numerical data, and the let's say argument is to see if you believe that there might be an effect of the boundary condition on the isothermal boundary condition that could have impacted the profile of skin friction. Is this correct? Yes.
Yeah. So we have performed using isothermal walls, and there is also the need to perform using adiabatic walls, because since the experiment was performed using both isothermal and adiabatic walls, so we need to do on that also. That also includes in the future works. So we are going to look into that and to look into the errors obtained by using isothermal walls separately and adiabatic walls separately.
Did you get the answer, or you want me to summarize it? Sorry? Yeah, okay. Okay, thank you very much. Please help me thank you again, the speaker. Thank you for the nice talk.
Thank you, sir. Thank you.